Hello, Professor Farouk. In today's video, I would first and foremost like to thank you for allowing me um, to do this study, this investigation, this mini research for my honors project, and sincerely thank you for everything you have taught us from the beginning of this class till now. So, without further ado, I would like to dive into the project. So for our project, I choose to do a missile launcher dynamic as a spring mass system. So we went ahead and tried to model a missile launcher as a second order differential equation using couple spring mass damper model. So from there we study we derive all our frequencies. We did the body plot, we did a plot of our displacement, rotational displacement, and vertical displacement for our movement. So we start by inventory all our doing nomenclature of all the variable we will need during our study. So once we have done that, we write a mini introduction. The introduction went over what really we were doing during the on the paper. So big takeaway was instead of studying all the parameters on the launcher system, which will be further complicated for most of us for our study, we decided to do a 2-degree freedom analysis of the launcher platform, which is a one vertical and one rotational motion. So the vertical is dealing by the zt, and the rotational delta t. So on the left side is the actual model of the launcher system we choose, but we simplify it to a more simple system that we will be able to analyze at my level. So from there, we start with mathematical modeling. So for the mathematical modeling, we just a simple second order equation of motion in the vertical direction that we did already, that as shown on the screen. And for our impulse, we choose a simple impulse ft, which is equal to f0 times e to the power minus at. So from there, we have also a rotational motion. The rotational motion is also shown here. From there, we try to write our transfer equation. For the transfer equation, we choose every condition at 0. So from there, we derive the transfer function. So once the transfer function was derived, as seen on the screen, we went ahead and start writing the state vector. So the state vector, as defined here, we also went ahead and compute the state space representation of s dot t is equal to ast plus but. So here is the matrix of our parameters a and b. These are shown. We have those written down. So from there, we choose one platform that I believe I was fascinated from trying to study. So this project gave me an opportunity to study that. So the platform we chose was the M901, a launcher station for the Patriot missile system. So from our investigation, we found that those are the value that match our variable that we chose earlier. So once we get those values from Army Recognition website, we went ahead and plug those values into our second order equation, and did a plot of our vertical displacement and our rotational displacement using MATLAB. So from MATLAB, those are the plot that we have. In blue is the vertical response, and in green is the rotational response. So from there, we find our rise time and overshoot, peak time, and we do the same thing for our rotational response. So those are the value. But what we found out was our overshoot was really high was extremely high was extremely high for the vertical displacement than the rotational displacement, and the rise time of the rotational response was higher than the vertical response. And again, from there we went to frequency domain analysis. So for the frequency domain analysis, we calculate our natural frequency, our damping ratio, damp natural frequency, get all the slope for our body plot. So we got for the body plot, we got a slope of minus 40 dB per decade. We did the same thing for the rotational mode of the launcher arm. We find for the body slope, we find almost minus 40 dB per decade also, and a phase angle of minus 90 degrees. So we plug those values into MATLAB, and then let MATLAB we wrote the code to do the body plot. So once we did those body plot, this is the body plot that this is the body plot for our study. So for the blue, and the blue is the magnitude, and the red is the is our phase angle plot. So we did the same thing for the rotational motion. The same thing for the rotational motion. For the slide, we have a slight difference, but nothing that a radius. So so our paper investigated the dynamic response of the Petri missile system, which was a fantastic, phenomenal, and we modeled that as a spring mass damper system. So the launcher platform was analyzed using system dynamic principle, such as modeling the launcher into second order equation system, second order differential equation system to characterize the vertical and the rotational motion of the system, and also how the stiffness, the damper affect those dynamic, the damping coefficient, the damping ratio, all those stuff came into our study. So by examining those transient response during launch, the study provide insight into structural vibration and stability control for advanced mobile defense system. So if we will have the opportunity to further this investigation, we will have the opportunity to study a THAAD system, which is a terminal high altitude area defense, also a mobile missile system, but can have a higher altitude of heat than the Petri missile system. Thank you very much for this opportunity, allowing us to do this project for our honor study, and thank you for everything you have taught us since the beginning of this semester, sir. Thank you once again, Professor Farrell. Goodbye. Thank you.